Welcome to AI Podcast. Today we're digging into a new EMNLP paper called Memory OS of AI Agent by Jiazheng, Kang and colleagues, with Ting as the corresponding author. Short version first, they built an operating system-style memory layer for language model agents, and it made long conversations more coherent and more personal, with big gains on a long dialogue benchmark.
Operating system style sounds cool, but what does that mean in plain language?
Think of an agent's memory like your workspace. There's the stuff on your desk you're using right now, the folders on the shelf you dip into every so often, and the filing cabinet where you keep personal and long-lived facts. Memory OS formalizes that into three tiers: short-term memory for the most recent turns, mid-term memory grouped by topic, and a long-term personal memory for stable details about the user and the agent.
So it is like desk, shelf, and cabinet. Why is this needed? Don't large language models already remember the conversation in their context window?
They remember what fits on the desk, but once the conversation gets long or spans multiple sessions, things fall off the edge. You get persona drift, forgotten preferences, and answers that contradict what was said a week ago. Lots of prior work tried to patch that with single tricks. Some methods save chains of thought like sticky notes. Others push everything into a vector database and use similarity search with a forgetting curve. And a few build OS like read and write operations. Helpful ideas, but each one alone leaves gaps in storage, updating, or retrieval.
Got it. So the pitch here is a full system rather than one clever widget. How do they actually make it work?
4 coordinated modules: storage, updating, retrieval, and generation. Storage is the 3-tier layout we mentioned. Updating moves information upward with simple rules. From short to midterm is a first in first out handoff based on dialogue chains. From midterm to long term is where it gets interesting. They group related dialogue pages into topic segments and assign each segment a heat score. Heat blends 3 signals: how often a segment is visited, how much interaction it contains, and how recently it was used. Hot segments graduate to long-term personal memory. Cold ones get evicted.
Heat is a nice metaphor. In practice, how does the agent find the right stuff when you ask a new question?
Retrieval runs in stages. It always has the latest short-term pages. Then it ranks mid-term topic segments by semantic similarity and a bit of keyword overlap, pulls the top segments, and within those picks the most relevant pages. Finally, it grabs a few personal facts from long-term memory, like your recurring preferences or the agent's own traits. The generation module then weaves the user's question together with those retrieved snippets to form the final prompt for the base model.
Give me a concrete example. What kind of detail does this bring back that a vanilla chatbot would miss?
Picture a user who mentioned a run in a wetland park 3 weeks ago and also talked about a fitness goal. Without a memory layer, that detail sinks into the archive. With Memory OS, the midterm segment for outdoor activities stays warm because it keeps getting touched, and the long-term layer captures the fitness goal as a personal trait. So when the user asks for lunch ideas today, the agent can say a friendly line like, "Remember your goal," and maybe suggest a lighter option. And if the user brings up weekend plans, it might recall that wetland park.
That sounds useful, but as researchers, we care about numbers. How did they test this and against what?
2 datasets. One is a multi-day simulated dialogue set where 15 virtual users talk to an assistant on multiple topics each day. Those conversations are auto-scored for retrieval accuracy, response correctness, and coherence by an external model called DeepSeek R1. The second is LoCoMo, which is specifically designed for ultra-long conversations with hundreds of turns. They compared against well-known baselines like TM, Memory Bank, MemGPT, and AMEM, and they ran tests on 2 different model backbones to check consistency.
And the headline results?
On LoCoMo with the stronger backbone, their system reports roughly 49% higher F1 and about 46% higher BLEU1 than the average of the baselines. On the multi-day dataset, it also leads across accuracy, correctness, and coherence. There is an efficiency story too. Because the system promotes just the hottest segments and keeps the prompt focused, it needed far fewer model calls than one of the graph-based memories and used roughly a quarter of the tokens compared with MemGPT in their setup, yet still achieved the best F1.
Fewer calls and fewer tokens is practical. Less waiting and less cost. Now, what about the long-term personal memory you mentioned? That sounds like it stores user profiles and traits. How do they describe that piece?
They split it into user persona and agent persona. User persona has a compact profile plus a knowledge base and a set of evolving traits, like interests or goals, extracted from conversations. Agent persona keeps the assistant's own profile and traits so it stays consistent in style and behavior. Both are capped queues so the system does not balloon, and they retrieve only a small handful of the most relevant facts per question.
I like the discipline of caps and promotion, but are there hidden assumptions here? Anything that gave you pause?
A few things. First, many capacity choices are empirical. How big the short-term queue should be, how many topic segments to keep, and the threshold for promotion. Those are tuned rather than derived from theory. Second, the system depends on the model to detect and summarize topics cleanly. There is no automatic merge or deduplication of overlapping segments yet, so some redundancy can creep in. Third, part of the evaluation relies on an LLM judge, which is common now but still benefits from human checks. And of course, storing personal traits raises privacy and governance questions that deployments will need to handle explicitly.
Those are fair caveats. On the flip side, what stood out as a real strength?
The unification. Instead of bolting on just a retriever or just a graph, MemoryOS treats memory like a first-class system with clear contracts. The heat rule is simple enough to reason about and adapt, and the results are consistent across different kinds of long-context tasks. They also released code, which helps with replication and extension.
If you were to build on this, where would you go next?
I would add adaptive controllers that tune the promotion threshold and the sizes of those queues based on load. I would add segment merge and split to keep the midterm store tidy over months. I would broaden evaluation with multiple judges and human raters and include privacy controls and consent prompts around long-term traits. Finally, I would push parity on fully open models so teams can reproduce results without depending on closed backbones.
Makes sense. Before we wrap, let me try a quick takeaway. MemoryOS treats agent memory like a real operating system. Keep a small desk, a tidy shelf organized by topic, and a cabinet for durable personal facts. Use a simple heat rule to decide what stays hot and what cools off. The result is conversations that remember you and stay consistent even when they get long.
Exactly. It is not flashy, but the discipline pays off. If you are building an assistant that talks to people day after day, this kind of tiered memory with principled promotion and retrieval is a strong blueprint.
All right, that is our coffee chat for today. The paper is MemoryOS of AI Agent from EMNLP. Props to the authors, especially Jiazheng, Kang, and Ting for a clear systems framing.
Thanks for listening to AI Podcasts. If you enjoyed this breakdown, share it with a colleague who is wrestling with long-term memory and agents. See you next time.